All right, so we're going to start Unit 4 on exponential and logarithmic functions. There are many of you that came in, especially during the prerequisite units, that you did not like logarithms. You just don't like them. And the sad part is logarithms are probably one of the most powerful mathematical tools that we have for explaining real-world relationships. So much of the world around you comes back to a logarithmic relationship. Things like cell growth, the rate of cancer, rate of money growth. All of these things go back to these relationships and they affect you directly. You've had direct contact with all of those things. So that's why we sort of give you the introduction to this. One of the things that's a theme in this class that I think you're starting hopefully to pick up on is that what you've learned in separation are actually connected ideas in a bigger system that we use and choose ideas to explain the world around us. So this is just that next step. If you think about it, we have done linear equations. We have done quadratic equations. We have done rational equations. We have done polynomial equations. We're now going to do exponential and logarithmic. Both of these are definitely Algebra 2 type topics, but those equations, all of those different areas are what we use when we create math models, which is the ultimate goal of what we're doing with our mathematics. For the most part, unless you're a big proponent of pure math study, you're going to get a degree in math. You're going to use applied mathematics in all of the different subject areas that you take in college, except for maybe some of the literary ones, journalism and things like that. Okay, so let's start out with a recall question. If I asked you to graph this without a calculator, can you do it? What shape is it? Does it open up or down? Is it standard or stretched or skewed? Standard. We know that because this is a 1 in front. The vertex would be located where? 3, 4. Opposite of what's in the parentheses, the same as what is outside of the parentheses. So you can know how to shift and flip. If you know those rules, today is going to be extremely easy for you. Okay? So, again, if we are graphing this real quickly, we would go right 3, up 4. We would put our vertex. It would open downward, left 1, right 1, and we would graph it. Yes? That's what I would expect you to be able to do coming into this unit without a calculator. Now, you also have been asked to graph functions such as y equals 2 to the x by hand in the past. Okay? So let's quickly make a chart. X, y. I'm going to use 5 standard values. I'm going to use -2, -1, 0, 1, and 2. If you plug -2 in for x, what do you get out as a fraction? Plug in -2 for x, I get 2 to the -2, or 1/4. Does anyone have a question why that's 1/4? Negative moves the base, squaring it turns it into a 4. What about -1 then? 2 to the -1. 1/2. 2 to the 0. Close. 1. This is an important one. 2 to the 0 is 1. How about 1? And 2? 4. Okay? What I've just graphed for you is going to be the root or home equation, what I've created the table rather, for 2 to the x. So we can come over here and graph this. I'm going to make this a very key point here. 0, 1. And then I'm going to plot the rest of them as is. So -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4. Now, the reason we go over exponential and logarithmic after rational is because exponentials have horizontal asymptotes. They have 1. So now when I go to graph this, it's going to be a curve that looks like that. All exponential functions have horizontal asymptotes. Now, the one thing to consider here is a recursive relationship, which means it's a relationship that goes on and on and on that has a pattern to it. If I look here and I turn this into, and you're not adding this to the table, I'm just putting it up here for note's sake. If I put a negative 3 in for x, what's my next fraction? 1/8, right? Then the next one would be 1/16, 1/32, 1/64. The fraction denominator is getting bigger and bigger, but the size of the fraction is getting smaller and smaller. So the relationship that we're seeing here is the fact that this is going to get closer and closer and closer and closer to the asymptote, but it will never be 0. That's why we have the existence of a horizontal asymptote. Questions? Now, next thing I want to put out there. Moving forward, we are not graphing with a table. Moving forward, we will not be graphing with a calculator for exponentials and logarithmic. It's all going to be based in the rules that we did in the warm-up. So we're going to take this key graph with this key center point, 0, 1. We're going to move it. We're going to flip it. We're going to do all these different things to it. So we're adding to our repertoire of the home graphs. We've had, I think, 6 so far. Absolute value, x squared, x cubed. Now we've got exponential. So here's our definition. I believe you have this in your notes. A lot of you see this as a whole lot of blah, blah, blah. An exponential function is defined as f of x equals a to the x. Okay? A has to be positive. A cannot be 1, because 1 to any power is going to give you 1, which is a horizontal line. And x can be a real number, so we're not talking about imaginaries. If a is positive, I have exponential growth. Looks like this. That's the function you just graphed. So 2, notice, was positive. X was positive. It creates this relationship with 0, 1 being a key point on the graph. Some math language ways we can describe the graph is that as x increases or gets bigger, so does y. Now, the only thing I want to mention here is the fact you spent a ton of time when you were learning about your, preparing for keystones. Remember talking about linear relationships? So you would have a line that looks like this, right? And maybe from here to here, this would be 2 to 1. Go over 2, up 1. Yes? We would call it a slope of 1/2. Yes? And what's important about the slope of 1/2 is that it is a consistent relationship on the line. So if I go from this point here, I would go over 2, up 1, over 2, up 1. It's always the same. Over 2, up 1, over 2, up 1, over 2, up 1, over 2, up 1. Every incremental change is exactly the same. It's off of this ratio of slope. That is not true with an exponential. In an exponential, I will have maybe a little bit of change, but the next time for that same amount of x, I will have a lot bigger change in y. Then the next little bit of x, I'm going to have an even bigger change in y. It's basically what you want your money to do in a bank account, right, over time? Would you rather have a linear bank account, or would you rather have an exponential? You'd rather have an exponential. Okay? I don't know if they ever did this with you in 7th and 8th grade. Did you ever do the experiment where they say, I'll give you a penny and double it every day? Would you rather have that or this much money per day? And you have to figure out which is better?
Yeah, I've done that.
Have you ever done that? No?
Except it was $1 million right off the bat.
Or you could either have $1 million, you could start with $1 the first day for a month, and then double it every single day. So like you get $1 the first day, then the next day you would get $2, then you would get $4. At the end of the month, which is a better situation. Yes, doubling is an example of exponential relationship because you're not incrementing the same. You go up by 1, then you go up by 3, then you go up by 4. Yeah? Am I just talking, or are you with me? Yeah? Okay, good, perfect. All right, so exponential, linear, that's all I wanted to cover for that little tiny foyer off of the truth. Domain. Same questions are still there. How far left? How far right? What are legal values of x? What is my range? Well, my range is going to be 0. Why do I have a parenthesis here for the range? Why don't I have a bracket? Yes, Greg. it's an asymptote, which means this will get closer and closer. It makes it a boundary of the range, or the y, but it will never take on the value of 0. My y-intercept, we have clearly 0, 1. My equation for my horizontal asymptote, all asymptotes are vertical and horizontal line equations. We can state that the graph is increasing and that it is continuous. When we go to draw it, we don't pick up our pencil. Questions on that? All right, super exciting. We're good. All right, now when I change the exponent to a negative x, I now have exponential decay. I want you to take a look at this graph. Exponential decay, I think one of the applications you would have heard of is probably carbon dating. You know what carbon dating is? The carbon in your body or in living organisms breaks down. Yes, the isotopes. It lets off electrons, basically. Are you with me? Have you heard of this? Yes? No? You've never heard of this? So basically, like, you know what a paleontologist does? They look at, like Pompeii, the little brush, and they go and take, I don't know, like clay pots out of the ground. That's always what I think of when I think of people who do that. Dinosaurs, that kind of thing. Yeah? When you find an organism that was once alive and isn't, you can take that and you can actually have it analyzed for the amount of carbon. We all have carbon in our bodies. They call it our carbon footprint, right? These things, have they been thrown around at some point? Well, anyway, the carbon in your body over time breaks down. Everybody's carbon breaks down at the same rate. Therefore, they can see how far it's broken down from the original form, and then they can date how old the organism was when it was alive. How long ago it died, basically, is the idea behind it. It's called carbon dating. And that is based on exponential decay models. Okay? So that's kind of a primary, kind of neat application of that when they date things. Like, what are those things the Egyptians had? Sarcophagus? What's it called? The Egyptians. No, and they, like mummies, they take them and they wrap them up and they put them in. What's that called? There's a name for a mummy. Is it a sarcophagus? Yep, that's the word, sarcophagus. So, yeah, so those are all carbon dated, etc. Once they pull them out. Kind of cool. Now, one thing I've highlighted, which you should also note, is the key point in this graph is still going to be 0, 1. 0, 1. Now, as x increases, y continues to decrease. Notice I still also have a horizontal asymptote. So my questions that I could ask you, what are the domain of this function? What is the range of the function? Tell me the y-intercept. What's the horizontal asymptote? And again, it is a decreasing graph that you can draw without picking up your pencil. Yes, ma'am. Okay, well, the graph is going to come down, right? And it's going to get smaller and smaller and smaller, but it's never going to be 0, so that's why I have it as 0. Like the y value, think of it like the floor of the graph. The floor of the graph is approaching, this is your y-axis, 0 here, but it never quite is 0. Like I'll never have this situation. This will never exist, but I'll get really, really close, like 1 over 1/32, 1/64, 1/28, etc. Questions? Yes. It will continue to get closer and closer and closer to the horizontal asymptote, but it won't cross it. And it continues to grow up to the left. Excuse me 1 second. Okay. So, real quickly, I'm going to put this in for the sake of the video. think about it, can either of these graphs ever take on 0? Well, if you think about what the graphs originally were, f of x is equal to 2 to the x, or maybe f of x is equal to 2 to the negative x. In both of those cases, you can never use exponents to generate a 0. What value of x, when you plug them in here or here, would generate a 0? None of them. If you plug in 0, what do you get? 1. So just as a fact that's associated with your exponents. Oh, by the way, would you like to know a fun math fact you can go home over dinner tonight and tell your family about? How old will you turn in 2017? You're going to be 16? Okay, so here's an example. She's going to be 16. Do you know this one already? What year were you born? What? 2001. Guess what it adds up to? That's true for everybody in the room. How old will you be this year? How old will you turn? Add it to the year you were born, and it adds up to the current year.
Yeah, but isn't that like an obvious thing?
Why?
Like you just subtract now's time from your age. That's when you were born. Wait. So what's the difference?
Well, my next question to you was going to be, oh, would this work for next year? It wouldn't work? Take how old you're going to be next year, add it to your birth year.
Like, if you're born in 2002, it wouldn't work. I thought you meant, like, next year being born. Like, wouldn't that not work? Because, like, if you're born in 2002. You add that to 2.
Day 15 added to 2.
That's 17.
Wait, what?
So at the end of the day, as a math fact, it makes sense, right? But did I blow your mind for just a second thinking about it? Right? Like, oh, real math. Math in the real world. Hashtag. All right, so that was my math facts for the day. What did you think? You like it? You should bring it up with your family. See if any of them think of that. Yeah. That might have been my Facebook status last night, and people might have said how that made their head hurt, and I really didn't understand why. Questions? No? Look, my joke put Ryan to sleep. I'm going to get him to laugh one time this year. I might have to fall down, or I might have to dance, but I will get Ryan to smile. Or laugh. Nope, nothing yet. Nothing yet. All right. Moving on. Now we're going to actually do the lesson. Are you ready? No more jokes about age. No more jokes about age. All right. Here we go. First shift we're going to talk about is when you add or subtract an exponent. Okay? So I'm talking about up here in the exponent when you add or subtract. Yes? You're with me? Okay? Please think of this as the parenthesis rule, because it is. So what did we do anytime we extracted information from parentheses? What did it reflect in the graph? What happened in the graph when we took information from in parentheses? It moved, we used the opposite sign, and we did what with the vertex, for example? How did it move it? Think back to the warm-up. Inside of parentheses, what did we do with the -3? And we did what with the vertex? Moved it. How did it move? Went right, didn't it? Inside and outside of parentheses are left and right shift. The same is true with this. Inside of parentheses are going to be left and right shift opposite of what it says. Okay? So, if I have a plus C, I'm going to move it left because we do the opposite. You can put parentheses here if you want. If I move it right, it's going to be a minus c. Minus c is going to be moving it right. So let's take a look at the first example we have. X plus 3, technically, think of it like parentheses. If you want to add them every time, that could be helpful to you. Our key point used to be 0, 1, correct? 0, 1. Don't write this, I'm just going to write it. What happens to my key point now? So the only thing I've plotted up here is 0, 1, which is the root equation. We're now going to shift it how? With the x plus 3? Left 3, right? Left 3? 1, 2, 3. Try that again. Okay, again, our home equation was 2 to the x. Here's my new origin. I'm going to go right 1 up 2. TV timeout. Does anyone have a question why I went right 1 up 2? If I plug 1 into here, my outcome is 2. 1 comma 2. So from my new origin, right 1 up 2. If I plug 2 in, 1, 2, 3, 4. If I plug in negative 1, 1 half. Negative 2 is 1 quarter. So I took the exact same graph from the warm-up and I shifted it to the left because this says plus 3. Questions on that? Yes. Okay, what was the key point in 2 to the x? The one that I made red originally on the other side. Your paper. 0, 1. That's like your vertex point. 0, 1 for all of these graphs. Yep. All right, next example. Here we go. We've got an x minus 3. So I'm going to take my key point, which I usually had at 0, 1 for my graph, and I'm going to shift it right 3 units. 1, 2, 3. It's now going to be here. Give me a new origin. Graph everything the same. Right 1, up 2. Right 2, up 4. 1 half, 1 quarter. Pulling it all the way through. You can also fill in the information about domain, range, and horizontal asymptote. We've talked a lot about this in previous units. What questions do we have? Yep.
So when you're getting to the other points, so for your x value, you're still doing -2, -1, 0.
But I'm counting off of that new crossed origin. Okay? Good question. All right, so let's talk about vertical shifts. Vertical shifts. Plus B at the end or minus B at the end is going to move it up or down with the sign. This rule is not any different. Any different. So if we look at our example, notice my root equation still is 2 to the x. So I want to think about that chart, -2, -1, 0, 1, and 2. 0, 1 as being your key point. On my original graph, I was at 0, 1, but now I'm going to count up 3 from here. 1, 2, 3. Notice I'm at plus 4. I'm not at plus 3. I'm shifting up 3 units. So that's going to put my new graph at plus 4. So I'm going to clearly indicate that that point is at plus 4, not plus 3. New origin is directly underneath. There's no change to the graph other than raising it up. So from my new origin, I'm going to count from here, right 1, up 2, right 2, up 4, left 1, 1 half, left 2, 1 quarter, and at 3, I'm going to have my asymptote. Plus 3 is my asymptote. Feeling good? Not feeling good. It goes through the origin. Good? I put Reeves to sleep. Rough crowd today. Because it's Friday. Alright, so real quickly, if you need to fill these into your notes, your domain, your range, and your horizontal asymptote. Alright, your next example, moving it down 3. Let's see if you can graph that one, a real basic one. I just want to see that you're able to do that without having to regenerate the table. Try the -3. So you're going to plot your point. The key point always starts at 0, 1. You go down 3, which puts it at -2. And -3 is actually the asymptote. Please remember that -3 the -3 doesn't tell you the location of the vertex, it actually tells you the shift of the asymptote. -3. Okay, so here's where I am. I'm going to take my point at 0, 1. I'm going to count down 3. 1, 2, 3. Puts it now at -2. Which means my asymptote is actually at -3. Here is my new quasi-origin. I'm going to count off of that little cross, which represents the origin. I'm going to go right 1, up 2, right 2, up 4, 1/2, 1/4. Connect them to make your curve. Good? All right, reflections. Now, again, these rules are the same as what you had before. If you have a negative in front of A, you have a negative in front of A, think about what you're doing. Negative A, it is going to reflect on the x-axis. Okay? If you have a negative in the x value, it's going to rotate around the key point. We have a reflection on the y-axis, but I want to talk about this idea for a second. Write that down, and then I'm going to make a correction to this so that you can see it in your head a little bit better. And here's my correction to this. I'm going to replace this reflects on the x-axis with a reflection on the horizontal asymptote. So what I mean by that is that if I have the horizontal asymptote is here, and you tell me the key point should be like right here, it's now going to move down here. The horizontal axis doesn't change, but that flip does change, the location of it. I'm I'm also going to change this to say that instead of having a reflection on the y-axis, I want you to reflect left and right on your key point. Okay? So what I mean by that is, if this is exponential growth normally, okay, that one would be a to the x. A to the negative x is going to go through that same point, but I'm going to reflect it around the key point. Does that make sense? Can you see that? So it's this same, it's like a cyclone effect this way, whereas I like to think of the horizontal asymptote like a trumpet. Here's why. So if I have this situation going on and I reflect down here, doesn't that look like a trumpet? I don't want to know what else it looks like. Let's just call it a trumpet and just leave it at that. Okay? Just saying. Yes? The reason why these say x-axis and y-axis is that these are the root equations, so that is true. But once you start moving these in the coordinate plane, these rules don't apply. But what I gave you will always apply. So a reflection on the horizontal asymptote, and then a reflection on around the key point. Okay, so you have the horn effect versus the cyclone. Ryan, not yet? No? Okay. All right, so if we take a look at negative 2 to the x, in your head, can you see 2 to the x now? Have you done it enough that you see it? Okay, so I've got 2 to the x. The negative is now out front, so that's going to be which effect? Right, it's going to be the horn effect. Okay, so I've got my coordinate plane. Here is my horizontal asymptote. I'm taking it from positive 1 down here to negative 1, and I'm graphing it so that it's the reflection. Taking this, folding it over the horizontal asymptote. What? Yes, that's what I'm doing. We're going to have so much fun putting all of these together. Are we good? Any questions? Yes. No, the horizontal asymptote stays. The vertex flips around it. Okay? So I went from +1 above to -1 below. All right, fill in your chart quickly. Domain, range. As you can see, my range is all the way from the ground to the ceiling of 0, but it'll never touch the ceiling. That's why I have a parenthesis for 0. Good? All right, so here's another one then. We can have 2 to the negative x. So I'm going to erase this for a second to unconfuse all of everybody. 2 to the negative x. That is an example of exponential decay. We did talk about that earlier. So think of it, you're going to rotate it around the key point. So here's my key point. Instead of having over 1 up 2, over 2 up 4, I go left 1 up 2, left 2 up 4. I just took the points that were here and switched them around, rotating it around the key point. 2, 4, 1, 2, 1/2, 1/4. Good? Know how to do it all? All right, let's put them together. Fill in your chart quickly, just to note it. If you didn't have it. Negative infinity to infinity, 0 to infinity, y equals 0. right, let's take a vote because I know how the vote's gonna go, but I'm gonna ask anyway. Do you want to do all 4 on your own and then check them, or do you want me to do them one at a time with you?
We do all four in the check.
Yeah, hopefully.
How about we do 2 of them and 2? I'll do 2, then you do 2. Compromise.
We're better than this.
Alright, how about 1 and 3?
Well, how about 1, 2, and 3? Is that what you said? All right, I'll tell you what. I will do 1 and 2, but if you just want to start working, I don't care if you ignore me. How about that? And then I'll give everybody time to do 3 and 4, and then I'll go over 3 and 4. So if you want to be with me, I'm going to do 1 and 2 explanation right now. Number 7. We're switching up the home graph. We're going to 3 to the x. Okay? 3 to the x. Ordered pair. 0, 1 is always going to be my key point in a plain old graph. 0, 1. When I go right 1, where do I come up at? Put a 1 in for x, you get right 1, up 3. Puts me here. What about 2? Go over 2, go all the way up 9, right? Up to 9. What's my negative 1 value? 1 third, 1 ninth. Horizontal asymptote here. And then I have my graph. Okay? So now what's tricky about these is that you have to keep this home equation in your head to do number 8. So in number 8, what are the 2 things that happen to my key point? They go right 1, up 2. So I have my coordinate plane. I take my original 0, 1, count from the original place. I'm going to go right 1 from there, and I'm going to go up 2. This is my new vertex. Plus 2 is going to be my horizontal asymptote. This is up to 3. At 2, I have this. Do I have anything else happening with the graph? No. Right? I don't have anything else happening. So I can just, I'm going to get rid of all this for now. 1, 2, 3, right? This is my new origin point. I'm going to go right 1, up 3. 1, 2, 3, 2, 9, 1 the third, 1 ninth. Notice you're using that root graph of 3 to the x. So counting off of that new little blue cross, which is on the asymptote. All right, you can do last 2. Good. One. All right, so just to make it clear, because these are just final answers, I'm going to mark the key point and its location and the asymptote so you can see it here. Okay, so this one's going to be at minus 2. you have questions, let me know. Number 10 is the Horn effect. Number 9 is the cyclone.
Okay, where was your original key point? 0.1, right? So I'm gonna move it down to, so that puts you at -1, doesn't it? Okay, okay, so that's, that, you just moved your key point forward. But now, what do you do with the negative up here? That's the cyclone, right? That's right. It would be like that. So instead of the exponential growth. Then I'm gonna go, you're gonna go left or left up 3. Oh. Right. Correct. Left, so off of that new cross origin, you determine this on your asymptote. Right underneath here. Yeah, you know what I'm saying? Yeah. Basically, I should probably write this up in a different color.
You're counting off of this origin, and this one you're counting off of this origin upside down. Anybody else? Questions? How do we do? When you start getting into the reflections, keep in mind this value here will always be your asymptote value, the vertical shift value. You will always have your vertical shift mandated by that asymptote value. Good? All right, you have your assignment. About 10 minutes left if you want to start it. If you have other work, if you need to go anywhere, please make sure I give you a pass. We're done. So tired. They're good. They're good.
I have my granddaughter.